As we have learned this year, forces are the basic building block of all physics. It is imperative for engineers to understand these forces in order to predict and calculate the world around them. A basic understanding of these forces builds up as we are able to predict more and more. Gravity is one of these forces that we can observe and affects us in everyday life. An example is this water bottle, which when you drop it, it falls until it hits the ground. There are a number of things that can be calculated from this simple task, such as potential energy, acceleration, and also how much time it would take for the object to land. Engineers and physicists can take the basic understanding of gravity and can apply it on a much larger scale of orbital mechanics. Any kind of orbit is created when an object is in a constant state of falling, but is moving too fast horizontally that the gravity of the object is not enough to pull it down to the surface. Newton's thought experiments are a good way of rationalizing this kind of thought. You fire a cannon off of an extremely high mountain, and it hits the ground a ways away. If you pack more gunpowder into the cannon, at some point the cannon falls for long enough that it continues falling around the object's curvature and reaches the point it started and continues in an elliptic orbit, the highest point being the apoapsis, the lowest point being the periapsis. Newton's laws serve as the basis for actually calculating space travel. Newton's law of universal gravitation states that the more massive two objects are, or the closer they are, the greater the gravitation. This, combined with Newton's second law that states force equals mass times acceleration, forms the basis for calculating orbits. As an object accelerates in a straight path around another object, the gravitational force of that object creates an acceleration towards itself and creates an orbital path. We can also learn more about orbits from Kepler's studies as well. From him we learn the elliptical nature of orbits, as well as how the orbital path affects an object's velocity. Kepler's second law states that a line joining an orbiting object to the other object sweeps out equal areas during equal periods of time. This means that the speed changes in an elliptical orbit so that the equal areas sweep out equal intervals. Some other variables you must be aware of are the size of an orbit, the shape of an orbit, and the location of an object in the orbit. These are 3 of the 6 orbital elements. Listed out, these are the semi-major axis, the eccentricity, and the time of periapsis passage. The semi-major axis is simply the half of the distance between the periapsis and the apoapsis of the orbit. The semi-major axis can be used in calculation to find the time it takes for an orbit to be fully completed. Eccentricity describes how elliptical an orbit is. Its value lies between 0 and 1. If the value of eccentricity is above 1, that means that the orbiting object has reached escape velocity. That means that the object has reached a velocity that it can no longer be held by the object's gravitational pull. Time of periapsis passage is used to determine the location where the object will be at any given point in time. This is reliant on the predictability of an object's flight path. From only one known point in time the object passes that point, we can determine the time of passage at any other point. Spacecraft operate at extremely high velocities and are subject to a multitude of different effects. As we get closer to traveling between the stars, speeds may reach significant fractions of light speed. This means that new methods must be developed, and unknown variables may need to be taken into account. Future engineers will need to face this problem head-on to tackle the problem of orbital mechanics.